a zero eigenvalue. And this will tend to put more weight on the fever vector than on other eigenvectors, but it includes all of the eigenvectors. And just to normalize this, to give a scale to U, we've chosen U so that the variance per node is 1. So the expected value of the Euclidean norm squared under this Gaussian process given by the number of nodes. Okay, so that's one way of thinking of the underlying Gaussian. Alternatively, you can think about it through a covariance matrix perspective, where this is a Gaussian, this is a draw from a Gaussian with mean 0, covariance C, and C is computed from the graph Laplacian by shifting it and raising to the power minus alpha. And some of the experiments will be done with the case tau equals 0. L is not invertible, but it is invertible if I work orthogonal to Q0, the first eigenvector of L, which we'll do. So we convert from the span of Q1 up to Qn minus 1. And then the constant C can be computed from the trace of L plus tau squared inverse to the minus alpha. Okay, so what does this Gaussian information tell you? I'm returning here to the voting records problem, in which this is simply correlation information from the unlabeled data. So here I've taken the voting information about every individual in the House of Representatives. They're partitioned here according to the Democrat and Republican. And I've taken 3 of them who vote very similarly. So their correlation is nearly 1, is 1. And this is a correlation under the Gaussian process I've just described. They are maximally correlated because they voted exactly the same. So these 3 individuals correlate with one another at correlation 1. And then you see how they correlate. They're all Democrats. Then you see how they correlate. What we're looking here is, we're looking at the correlation of the sign of the Gaussian process. And the sign function is very important here because it's the sign function which I use to connect real value processes with labels. So here I'm looking at the sign of this Gaussian process and its correlation structure. So these 3 people all voted exactly the same. They're Democrats. And here you see their correlations with other Democrats in terms of the sign is on average much higher than their correlations with Republicans. Okay? So this is just to show you that this Gaussian process, which is built from the graph Laplacian through the unlabeled data, builds correlation information about the similarity and dissimilarity between different nodes of the graph. So our purpose is to take that correlation information and use it to spread the labels on Z prime to the entire graph. Okay, so now I want to revisit the probit model from this Bayesian perspective, where the prior is the Gaussian I've just been telling you about, and then the likelihood underlying the probit method can be thought of in the following way. That the assumption is that the label data is found by computing the sign, so +1 or -1, depending on positive or negative. So SIGN, not SINE. The sign of the latent variable u, which is real valued, with noise added to it. And the noise is Gaussian with mean 0 and variance gamma squared. So with that prior and likelihood, you can apply Bayes' theorem and compute a posterior. And the posterior has a density, the Begg density, which is the exponential of the probit objective function that I showed you earlier on. There's a lot of information in here, but the key thing I want you to notice is that I've highlighted the form of the likelihood here, because if I now show you the level set method, it's almost identical, and I want to just highlight to you the sense in which it differs. In the level set method, the likelihood, the assumption behind the level of the likelihood is that we take the sign of the latent variable u, which is real valued, and add noise to it. Whereas in probit, the assumption is that we add noise to the latent variable and then take its sign. So the only difference between the level set method and the probit method is the order in which one adds noise and takes the sign function. And therefore, it should not be surprising to you that if the noise is small relative to the latent variable u, these two methods will be closely related. And I'll show you in a second that they are. But in particular, I'd like you to remember that I've normalized the Gaussian process, which is the prior, so that the u has mean 0 and its variance is 1. So the typical size of u here is 1, and the noise here is a standard deviation gamma. So if gamma is small, it should not make that much difference whether you add noise and take the sign, or whether you take the sign and add noise. So in that sense, which will turn into a theorem in a second, the level set and probit methods are closely related. Questions?
So what was with the tau shift that you had in the earlier slides? I don't feel like you...
I didn't really go into it in great detail.
Yeah.
For most of this talk, you just assume tau is 0.
Okay.
There are reasons extraneous to this talk with hierarchical methods where it's useful to include tau.
Okay.
Maybe if you ask me afterwards, I can tell you about them. But for the purposes of everything I'll describe in the talk today, just think of tau as 0.
Cool.
So therefore the C, the covariance, is simply a negative, possibly fractional power of the graph of Bayesian
Okay.
with a scaling constant. That's sufficient.
Thank you.
Thanks. Okay, so let me tell you two theorems about this. One relating to the optimization approach and one to a probabilistic way of thinking. So the first thing is, from the point of view of infimization, both posteriors in the probit and level set method case, both of them can be written as the exponential of an objective function, which is quadratic, that's from the Gaussian prior, plus a penalty term that drives the sign, roughly, drives the sign of W towards the labeled data plus or minus 1. And I have two facts. One folklore from the study of the probit method, and easily proved, is that the objective function for probit is convex. The second fact is that the level set objective function doesn't obtain its infimum. So there are infimizing sequences for this objective function which tend to 0, but at 0 the infimum is not attained. And there's a number of things to say about that. That's a general problem that plagues many optimization approaches to inverse problems based on the level set method. And there are lots of ways to get around it, but none of them, in my opinion, are very satisfactory, except for the one I'll describe on the next slide, which is a probabilistic method. But the second thing is that although this is convex, since these problems are related very closely in the small gamma limit, the lack of attaining of the infimum of the level set must show up somehow, making the probit optimization difficult, and it does. Okay, on the other hand, if we look at this from a probabilistic point of view, which I like, this avoids the lack of infimum being attained, because putting down an underlying probabilistic structure sets a scale. So let me just say, the problem here is that W is a real value function, but the only data we have concerns really the sign of W. And so the issue of scale is really important. I've scaled W so it has size 1, but in the optimization problem, that sense of scale is lost. When we go to probability, imposing a prior sets a scale, and we can formulate both probit and level set as Bayesian probabilistic problems, and they both have a common limit. So if we look at the weak limit of their posterior distributions in the small noise limit, they converge to a very simple probability distribution, which is what I've stated here. So the prior is this Gaussian, where C is an inverse power, a scaled inverse power of the graph of Bayesian. That's the prior distribution. And the posterior is found simply by multiplying this by an indicator function. And the indicator function is the indicator function of the set A. The set A, where U agrees with the sign of the labeled data on the subset Z prime of indices where we have labeled data. So that's a very nice, clean probabilistic problem, We have a Gaussian that reflects the unlabeled data and correlation between the vertices on the graph, and then we condition it so that the sign of the process agrees with the labeling. Not only is that a nice clean formulation, it links those two existing methods which come from completely different backgrounds, and furthermore, it's a very straightforward formulation, that one can sample, to produce algorithms, which I'll come to in a moment. I also want to make a point that this is closely related to one of the original papers in this area that I mentioned earlier by Zhu, Garamani, and Lafferty, which solved the problem in which u was not conditioned on the sign of y, but was actually conditioned so that u equals y on the labeled data point. So that's a form of kriging on a graph. It's Gaussian process regression. Then you might say, well, why not just stick with that? But to me, this is not a good model of the likely relationship between unlabeled data, which is typically real valued and d-dimensional, and labeled data, which is categorical, and to assume that the process derived from the unlabeled data actually takes the value of the labeled data is, from a modeling point of view, not satisfactory. Whereas the conditioning on the sign, to me, is a more satisfactory modeling assumption. Okay, so what I've done so far is formulated a number of different problems through both, two different methods, probit level set, through both optimization and Bayesian probabilistic formulation, and shown you that they're linked. There are other methods, such as the method developed by Andrea Bertozzi, which uses Karn-Allen or Ginzburg-Landau penalty on the graph to approach this problem, and that they can be looked at in a similar perspective. So although I've restricted to this talk to level set and probit, there are other methods that one can study by this approach. I've shown you a Bayesian formulation which is unifying. It has a number, though, of other advantages, which is that it gives uncertainty information. Well, firstly, it can be sampled efficiently, as I'll now show you, and gives uncertainty information about classification. So I want to tell you a little bit about that. So, algorithms. This is a very simple algorithm to sample. Let me just remind you of the general formulation. All of the problems that I'm talking about today have this form, where I'm interested in sampling a probability distribution on a real valued variable w or u, given y, which has this form, and j is the sum of a quadratic, which can be related to a Gaussian, and a non-quadratic term. This particular method for sampling that probability distribution makes proposals which respect the quadratic structure, the unlabeled data, and then accepts or rejects to reflect the labeled data encapsulated in phi. So in broad terms, point 2, I'm going to make here a Markov chain UK, which is reversible, which means ergodic, implies ergodic under some additional assumptions which are verifiable here, ergodic with respect to the measure of interest. And the proposal is a linear combination of the current state of the Markov chain UK with a noise which is generated from the Gaussian process described prior. And the combination is such that the sum of the squares of the coefficients is 1. And with that particular combination, you have the nice, simple acceptance probability that you accept with this probability the minimum of 1 and the exponential of the labeling penalty evaluated at the current state minus the labeling penalty evaluated at the proposed state. And if you accept or reject that probability, then you generate a Markov chain UK, which is, as I said, ergodic with respect to this probability distribution. Why do we use this method? There are no derivatives for phi, so I don't want to use any method that involves derivatives because it has the sign function in it. It is not, therefore, nice to compute derivatives of. And this method, for given acceptance probability, beta, which you would need to achieve, the beta that you need to obtain a given acceptance probability is independent of the size of the graph. So this method scales well in terms of the number of steps required with respect to the size of the graph. And furthermore, you can exploit properties of the graph for Tracy, and you can use the Nystrom method to compute its eigenfunctions approximately and cheaply. So let me just give you an example of what we get out of this. So this is the MNIST data set, which is a set of digits, all of which are handwritten, digitized, and they're all classified according to 0 up to 9. And here I'm looking at classification of 4s and 9s. And what I'm showing you here are the most uncertain digits, because there's an uncertainty of measure associated with this probabilistic formulation, and the most certain digits. So you see that this uncertainty quantification not only labels things, but correctly identifies, this, for example, that looks to us like a 7 was labeled as a 4 in the data set. This is close to a 9 and so forth. So the uncertainty, and I'll get to this in more detail, the uncertainty that one can determine from this Bayesian approach is useful in attaching certainty or otherwise to classification data.
Sorry, I can ask what happens because so initially you try to do the maximum likelihood estimation, and then you use the Bayesian framework to sample. And this is what you get by what kind of probability sample? Or?
Yeah, no, this is what I get by compute I have a probability distribution on the real value variable on the graph, whose sign gives me a label at every point on the graph.
Okay.
So that's a random function, and therefore the sign, SIGN, is also a random function.
Right.
So at every node, I have a random function, which is plus or minus 1,
Right.
and then I can compute its mean. If its mean is very close to 1 or minus 1, it's a very certain classification. And if it's very close to 0, it's a very uncertain classification. So for each node I can classify by how far I am from 0, the certainty or uncertainty.
So the first row is one.
Those are the 10 most uncertain, and those are the 10 most certain. Thank you for asking that. And that's something we can do more generally with this methodology, and I'll show you another example in a second. Just a couple of words on computing here. So I'll get to a problem in a moment with roughly 500,000 nodes. Computing, and the L is a full matrix. Computing the entire spectrum is expensive. The spectra, as you see here, often saturates. And you can do a number of approximations. For example, truncating the Calhoun-Loewe expansion, which is a way of sampling the Gaussian after L terms, or better, using the saturation to approximate the Calhoun-Loewe expansion, which means you don't need to compute eigenfunctions after the saturation point, and reduces the computational cost of the Gaussian part of this method. This example, which is again the voting records example, shows that in black is data computed with full computation of the spectrum. In blue is computation based on truncating the spectrum after L much less than N terms. And the red is an approximation based on using the saturation, the empirically observed saturation of the spectrum at the value 1. And what you should observe here is that the black and the red are very close to one another, which tells us that the red approximation, based on using saturation of the spectrum, is accurate, whereas the blue, which is based on throwing away part of the spectral information, has more inaccuracy associated with it. Again, following up from the previous question, what you're seeing here is a measure of uncertainty. The closer you are to 1 or minus 1, the more certain you are. The closer you are to 0, the least certain you are. And so the method which truncates is overconfident about classification. Okay, this is a problem which is based on spectral imaging data of gas in the background, and the objective spectral data is of dimension 129. There are 300,000 data points, and the objective is to classify whether one has gas or background. The gas is poisonous, so that's why it's important to be able to classify. And the color coding here, blue is background, yellow is classified accurately, and red is classified as being, yellow is classified as gas accurately, and red is areas of uncertainty. So over and above standard optimization methods, the point of this simulation is to show you that the Bayesian approach, which we compute quickly, also gives us uncertainty information that is useful in problems of this type. Okay, I'm going to finish in the last few minutes by talking about large graph limit, and I want to first summarize this key theorem from this paper of Stuart and Garcia-Rios, who is a student at CME. And the assumption here is that the unlabeled data, called xj, is sampled IID from a density rho supported on bounded open subset D in RD. And what they look at is the limit that the number of unlabeled data points tends to infinity. And in the sense of gamma convergence, which I won't describe, but many of you will be familiar with, gamma convergence needs a metric, and they introduce a very clever metric, which I won't describe, but which is an optimal transport type of metric. But it deals with the fact that the graph Laplacian is defined with discrete points, whereas the limiting object is going to be a differential operator. It deals with this in a very clever way. They prove gamma convergence of the quadratic form defined through the graph Laplacian suitably scaled to a quadratic form defined by a differential operator. Okay? So I like this, and this is the motivation for their work, because this formulation to a differential operator, I think, enables us to see a lot of structure that's lost in the data in general. And the differential operator is elliptic, divergence form, homogeneous with respect to rho. That's because I'm working with the normalized Laplacian, and has the form you see here, with these flux boundary conditions on u divided by rho to the half. And L is self-adjoint with respect to the L2 space, weighted by density rho. Okay, what we can prove in work with Stuart and Thorpe, who is his postdoc, is to prove a continuum limit of the probit algorithm under the same scalings that they use, where we choose the covariance operator to be the scaled graph Laplacian, as discussed in early questions. You can think of tau as being 0, raised to the power minus alpha. And we then get a nice PDE optimization problem. And that has this form. We have a quadratic form here, defined through this elliptic differential operator from the previous slide, raised to the power alpha. So this you can think of as a Sobolev penalty, but not standard Sobolev space, because the sampling density of the unlabeled data enters the differential operator, but it's Sobolev-like, and indeed equivalent to Sobolev norms. And then phi p is a penalty function